Welcome back to our lecture series on Physics 1. Today we're going to cover everything between displacement, velocity, acceleration, and all of the beginning topics in kinematics, which is generally the first unit in Physics 1. So before we talk about any of the ways that objects move, one thing we need to cover is the concept of reference frames, which I feel like is a little bit undercovered and not quite solidified in the minds of a lot of physics students before they start studying physics. So one thing you need to understand about the universe is that every observation or measurement of position, distance, speed, acceleration, anything like that, must be made by someone or something from a certain frame of reference. So we're going to hop onto a train for a quick example. So imagine that this is us, and this guy is walking toward us at 5 kilometers per hour. See, we're seated down and we are not moving. So from our perspective, we're motionless. And so from our frame of reference, our speed is 0 and our position is not changing. Okay? But the train we're in travels at 80 kilometers per hour. All right? So from our frame of reference, this guy is walking toward us at the 5 kilometers per hour. But from some perspective outside the train, we could clearly see this guy walking and changing his position in this direction by over 80 kilometers per hour, while we are also moving at least 80 kilometers per hour. So, if we're looking at the two of us from outside the train, we are moving with the same velocity as the train, and this man in orange is moving with the velocity of the train plus some velocity that he's adding on top of that, right? So, is he traveling at 5 kilometers per hour or is he traveling at 85 kilometers per hour? Well, both things are true. It just depends on what your frame of reference is, right? And so how do we actually define frame of reference when we're doing normal physics? Well, when we're discussing the motion of objects in everyday life, it's usually implied that we mean with respect to Earth. But of course, Earth is moving too, and therefore Earth is also just some big train that we're all on. Now, in physics, it's exceedingly important to specify a frame of reference anytime you're doing a physics problem, okay? And this is typically done by drawing a set of coordinate axes, right? And so what that does is it tells us what direction is positive x, what direction is positive y, negative x, negative y. All right, so placing an object on a set of coordinate axes when you're discussing it physically, this allows us to identify a lot of things about the object, all right? It allows us to identify the object's position with respect to some origin point. It also allows us to specify exactly what direction in which it's moving if we have some velocity or acceleration vectors. It also allows us to specify exactly what direction the object's moving if we have some velocity or acceleration vectors tied to it. That said, if we have those vectors tied to it, using the graduation on our coordinate axes, we can find the magnitude of any velocity vectors that are tied to it. Okay, so now that we've discussed how frame of references work and how we actually set frame of references, let's establish the difference between distance and displacement. This is really a cornerstone to Physics 1. All right, so by definition, displacement is how far an object is from its starting point. And distance, by definition, is how far an object travels. Let's go for a walk really quick. Let's imagine that we started at some origin point here, and we walked 70 meters east, right? Then we decided to turn around where we walked 30 meters west. You can see that here in the illustration. In this scenario, our distance was 100 meters because 70 meters plus 30 meters is 100 meters. But our displacement is only 40 meters because when we were done, we were only 40 meters away from our starting point. And that is the difference between displacement and distance, and so much physics is built on top of that difference. At least for displacement, let's establish a mathematical definition. We're going to do that a lot in this series. Delta x, we're going to label displacement as delta x because delta just means change, and x is just a variable for position. So change in position is what we're going to call displacement, is going to be defined as x sub f minus x sub I. All right, that sub f means our final position, and that x sub I means our initial position. And if you notice from our graph, our final position was 70, all right, and our initial position was 0. So if we took 70, all right, and we subtracted 0 from it, we would get our displacement, which was just 70, okay? Now, delta x is our displacement, x sub f is our final position, and x sub I is our initial position. Moving forward in this series, you're going to see that the subscript f generally means the final value for something, and the subscript I generally means the initial value for something. All right. Distance is always just the sum of the magnitude of all the changes in x. So in this case, 70 plus 30, that was our distance. Now let's talk about average velocity. Now, both velocity and speed are terms that you'll hear all the time, and they both refer to how fast something is moving. But they are both also distinguishable in a similar manner to displacement and distance. So first off, let's discuss speed. Speed simply refers to the distance an object travels in a given time period, regardless of what direction it's traveling. An object's speed can vary from moment to moment, but we can still calculate its average speed over time in the following manner. Average speed is equal to distance over time. Distance traveled over time elapsed. So if we have some total distance, like 100 meters, however long it took us to complete that 100 meters, we would divide 100 meters by that time period in seconds, and that would give us our speed, or at least it would give us our average speed. Now, for velocity, velocity works in the same way, as it can change moment to moment, but its average is measured using displacement instead of distance. So here where we have distance in our average speed equation, then we're going to have displacement, that delta x, in our average velocity equation. So v is equal to delta x over delta t. All right, so that's average displacement. And when you see some variable with a straight bar on top of it, that typically means the word average. Instantaneous velocity is a little bit different from average velocity. So if average velocity is displacement over some time period, instantaneous velocity is the displacement over an instant. Your car speedometer is always trying to show you your instantaneous velocity, and it's always changing because your instantaneous velocity changes from moment to moment. Now, when you're using a device like a speedometer that can tell you your instantaneous velocity moment to moment, if you were to record those velocities over some time period, you could plot that data on what we call a velocity versus time graph. All right, so you see here on the screen a velocity versus time graph of the velocity of maybe a car over some time period. All right, it started at 0, as a car might do, all right, and it went up to about 50 miles per hour, and it was traveling at 50 miles per hour for a little bit, but it started to slow down, and for a while it was traveling at 20 miles per hour, all right, before it eventually came to a stop. All right, so the instantaneous velocity of that car was changing throughout this 30-minute time period or half-hour time period. But regardless of how much the instantaneous velocity changed, the object always has some average velocity. And if you have a graph like this, then you have what you need in order to find it. The area underneath the instantaneous velocity graph, the area underneath this line here, is always going to be equal to the area under the average velocity line. All right, so this area, I'm showing you the area under the average velocity line, is always going to be equal to this area. It's an interesting thing about studying physics graphically. Now let's talk about acceleration. So by definition, acceleration is just how fast velocity is changing, and also in what direction. And of course, velocity can be changing at different rates from moment to moment, but we can always calculate average acceleration of an object over some time interval in the following manner. Average acceleration is equal to change in velocity over time elapsed. So it looks very similar to the average velocity equation, but instead of displacement on top, we have change in velocity. So average acceleration is equal to change in velocity over change in time. Now, we can also have instantaneous acceleration, of course, and this is how fast the velocity is changing over a specific instant. And instantaneous acceleration can be changing from moment to moment, but we can quantify it if we have a velocity versus time graph with some data on it, all right? So if we had the same velocity versus time graph that we were dealing with in the previous page, then we could always find the instantaneous acceleration by at any point on this graph. If we were to identify some point, right? Identify some point and draw a tangent line to that point. And a tangent line, of course, is a straight line that touches or attempts to touch only that point. Now, if the change is constant, then it is going to be touching the points around it, but it is a straight line that is touching only that point and is following, or at least attempting to follow, the slope of the graph at that point, okay? So if we were to find the slope of this red line, that would actually give us the instantaneous acceleration of the object at that purple point right there, or that about at the 0.2 hours point. So I wanted to make a comment about deceleration for a minute because there's a common misconception. So when an object is slowing down, we say it's decelerating. But deceleration does not mean the same thing as negative acceleration. All directions in physics depend on your frame of reference, and that's why we started this set of notes off with a frame of reference. So if this is my frame of reference, where this direction is positive x and this direction is positive y, that means that this direction must be negative x. Then we can say that this car, which starts off at 15 meters per second and decelerates to 5 meters per second, experienced some negative acceleration. So it decelerated due to some negative acceleration. But if the car was traveling in the opposite direction, and it was initially negative 15 meters per second and decelerated to negative 5 meters per second, then it still decelerated because the magnitude of its velocity decreased, okay? It slowed down, quote unquote. But the acceleration in this case is actually positive because the direction of acceleration doesn't actually depend on whether the thing is speeding up or slowing down. It depends on what direction the object is moving, all right? So just keep that in mind and take a look at this page a little longer if you really need to kind of let what's going on here sink in, all right? I've given you I've actually solved out the acceleration for you based off of its velocities and its time period so that you can see an example of that as well. So that's all we have for this topic. This is just really setting up kinematics. We talked about displacement and distance, the difference between those two, all right, speed and velocity, as well as acceleration and instantaneous acceleration. We got to see a velocity versus time graph, and that's going to be really important. We're also going to see acceleration versus time graph and distance versus time graphs in the future. All right, guys. So can't wait to see you in the next one. All right.